All right.
Take the full
Good
semester,
afternoon.
fill the classes, or just pay it part
I
of the
posted the
classes.
grades on the Canvas, so I'm gonna keep the exam at my friend. If you have time, you work on the exam problem. So let's continue. Let me finish the example that we started last week, and then move to the fluctuating stress. So it has many different, so make sure that you are following and don't get lost.
No.
Okay.
Just, no, thank you, I would like to return this. I don't have a gift receipt.
So we were working on this example. We were given with this driving shaft, which is rotating. One load is applied here. The dimensions and the material of the shaft was given. We were asked to estimate the life of this part, for this driving shaft. First, what we did, we tried to find the critical section. There were 3 candidates for the critical section. Section Section E with the maximum bending moment. Section B with this discontinuity on cross section, which is gonna give us fatigue concentration factor. It's gonna increase the actual stress by the factor by this multiplication. So nominal so section B, section E, and section C also there are candidates. So we calculate bending moment, and then we calculate sigma at section E, sigma at section B, and sigma at section C. Kf for this was 1 because there is no discontinuity, multiplied by 167.8 megapascal with 1.678. Sigma B, we could get Kf equals 1.53 times 216. We got 330.48 megapascal, and this one, the factor of fatigue concentration factor was 1.49 times 177.3, times 119, we got 177.3. So then we compare these three. This stress is the highest, so section D is going to be the critical section. So we should do the analysis for the rest of the analysis for that section. I need to find SE, endurance limit, and compare with sigma B. If endurance limit is greater than sigma B, meaning the normal stress, the maximum stress is applied to section B is less than the endurance limit, so we have infinite life. So this mechanical component can run with no failure, but if SE is less than sigma B, then we have finite life. Then we should find the number of cycles. Before failure. This is how we can work on these types of the problem. To find SE, we should look at these factors: surface finish, size, temperature, yes, the surface KB was a load factor. So. Load factor or what? Size factor. KB size factor of C is load factor. Load reliability KE, this is reliability, this is temperature, and Kf is the other factor. This case is different than this. This is the fatigue concentration factor times S' E, and S' E is half of S ultimate. The material was 1015 cold ground. $10.50, sorry. So S ultimate is 590 megapascal, and yield strength is so we did calculation and we could find SE equals to 236. This was the last thing that we derived on, I guess, Monday class. So the endurance limit for this component made of this material is 236 megapascal. Compared with the stress that we have 330, and 230 is less than 330, so we have finite life. Now we can find the number of cycles before failure occurs. So basically we are looking at the SM curve. S and this is SE, F, S ultimate. So the S stress that we have, it's gonna be greater than SE. As you see, it's 330. So I will find this point, and then I decide which segment should be applied, either this one or this one. So this point is F, S ultimate. F. Figure 618. Fatigue strength factor, depending on the S ultimate, you can read value of the F. S ultimate is given in megapascal. If you want to change megapascal to kpsi, you can divide by the factor of 6.89. So you will get about 100 kpsi. Ultimate from megapascal to kpsi, you can divide it by 6.89. So 100 is here. It's about 0.84. It's more than 0.84, but I just 0.84. it's slightly greater than 0.84. So I use 0.844. So that's 0.8444. So 0.844 times S ultimate, which is 690, I will get Please someone calculate this for me. Should be.
It's 582.36.
Thank you. 582.3. Okay. 582. It's gonna be this point. So the stress that I have is 330. So it's this one SE is 236. This one is 582, and the stress that I have is somewhere between these two. So I'm gonna use this line. This line, SF is A n power B. This is 330 megapascal, 0.48 times 10 power 6 megapascal, A and B. If you remember what was the value for A and B. A would be F S ultimate squared divided by SE is 582. Yes.
Why is it, so we have up there SUT is 680, and then SY is
680, thank
500,
you.
which, okay.
So would you do it again?
$573.92.
Thank you.
Yep.
No, you're good. You're good.
10 power 6, it's megapascal squared divided by 236, 10 power 6, it's gonna be 1437, 10 power 6, which is 1437 megapascal. For the A, B, B would be negative 1/3 log of 0.844 times that is going to be 573.9, 10 power 6 divided by 236, 10 power 6, I will get negative 0.1308. A and B are given. I'm looking for N. So N, if you remember, would be whatever is the S stress, which is 330.48 megapascal divided by A, 1437 megapascal power 1 over B. You end up to 75,000 cycles. So it's gonna run about 75,000 cycles. If the speed of the shaft is given, you can figure out after how many hours you will see failure. Makes sense? Any questions so far? All right. In all problems, before I go through the new topic, the sigma max that we calculate was 330.48. 330.48. So what if sigma was 600 megapascal? If sigma, suppose then based on the loading that we had on the problem, I could find the sigma equals to 600 megapascal. If you look at the yield strength is 590. So basically the stress, the maximum stress is greater than the yield strength. So we are going to have the failure due to the static failure. So we have two modes of failure, due to the fatigue, due to the static failure. So since we have yielding occurs, no need to do failure analysis for fatigue because it's already failing due to the yield. So make sure that you check this one also, because you may end up the stress greater than yield strength, and you do the fatigue analysis, and it looks good, but it's not, because you might see the failure due to the yielding. All right. In all examples and the materials that we covered so far on fatigue analysis, we assume that we have completely reversed stress cycle. It means, if you remember, if you plot sigma versus time, it's going to look like this, completely reversed. A sinusoidal function, it's moving or oscillating over the time. So if you look at this completely reverse cycle, so what if we have the fluctuating stress, meaning it's not completely reverse cycle? If I have something like this, fluctuating stress cycles versus completely reverse cycle. Whatever we talked about that, including S and curve that we derived, it's valid for completely reverse cycle. What if I have a situation with fluctuating stress cycles, meaning it's not oscillating about this axis, it's going to oscillate about a different axis, or some different example for fluctuating stress. We call it repeated, but it's still fluctuating. So repeated stress cycles, it's example of fluctuating stress. So I'm going to define some terms. One, as a sigma max. If I ask you what would be the maximum stress here, you can label this. What would be the sigma mean here? It's going to be this one. For completely reverse cycle, sigma max equals to the absolute value of sigma mean for completely reverse cycle. Here, sigma max is going to be here. Sigma mean is going to be right here. In completely reverse cycle, what we did, find sigma max. We find that sigma max compare with SE. I will find sigma max, I compare with the SE. You know that if SE is less than sigma max, or sigma max is greater than SE, we are going to have finite life, or failure occurs after some number of cycles. And we should be safe if SE is greater than sigma max. No failure or infinite life. This is what we did for completely reverse cycles. But for fluctuating stress cycles, it's going to be different. We are going to define two terms to study the fluctuating stress. One term is sigma A, or alternating stress component. Sigma A is defined as sigma max plus minus sigma mean divided by 2. Yes, it should have an absolute value as well. Yes, and one absolute value. So alternating stress component is defined as sigma max minus sigma mean divided by 2. Now for completely reverse cycles, if I want to find sigma A, it's going to be sigma max minus sigma mean is negative value of sigma max. So sigma mean is going to be negative value of sigma max divided by 2. Sigma max minus times minus is going to be plus 2 sigma max divided by 2, it's going to be sigma max. So this value is going to be sigma A. Here, if I want to find that, this minus this is going to be this one, divided by 2 is going to be half of this, which is this value, as you see on this figure. Sigma max minus sigma mean, I just subtract this portion. I left with this one. I divided by 2. I'm going to get that portion of it. Okay. So the second term that I would like to define is the mid-range or mean stress component. Is defined as sigma max plus sigma mean divided by 2. Mean, it's just representing the meaning of the mean. So you should just find the mean of stress values. For completely reverse cycles, sigma m would be sigma max plus sigma mean is negative sigma max plus minus, it's going to be 0. So the mid-range or the mean value of stress is going to be 0 for completely reverse cycles. But for these cases, sigma max plus sigma mean, you will get some values. This plus this divided by 2, you will get sigma m, some non-zero value. And what is making complete reverse cycle different than fluctuating stress is mid-range. For complete reverse cycle, always sigma m is equals to 0 because sigma max equals to negative of sigma mean. But for fluctuating stress, it's gonna be different. And we get some value for sigma m. So then this curve is not valid anymore because another term is showing up. We should see how can we deal with these types of the problem, and the rest of chapter 6 is talking about this type of stress component. Is that clear? All right. Any questions so far? So we no longer have completely reverse cycle, we have fluctuating. So basically we have sigma A and sigma M. So this is not working anymore. So if you remember when we had static failure analysis, to predict the failure, we introduced some failure theories for ductile material and for brittle materials. We covered all of them, and we know how to use them in any problem. But for fatigue problem, when we have fluctuating stress, meaning we have sigma m showing up in the problem, we need to introduce some failure theories. So fatigue, I'm going to introduce some fatigue failure theories. So these theories, they are going to help us to predict the failure. So similar to what we did on static failure, I'm going to do this for the fatigue problems for fluctuating stress. For non-fluctuating or completely reverse cycles, we know how to do that. For fatigue failure theories, we define two axes. One axis sigma m, or later on you will see it's going to be Sm, or whatever is that. It's representing the mid-range or mean value. The y-axis is representing sigma a or Sa, alternating component. So for now, I'm going to use only sigma a and sigma m. But later on, you will see we end up to Sm and Sa. The first theory that I would like to talk about that is modified Goodman theories, or sometimes they call Goodman theory. This point is representing the ultimate strength of the material, whatever is the material of the component. You find S ultimate here. You find SE, endurance limit. Just similar to the approach that we did previously for completed reverse cycle problems. So you will find SE and S ultimate. Then you connect these two. This line is representing a good mass or modified good mass line. So for a given problem, you will find sigma max, sigma mean. So you can find sigma A and sigma M. So for a given problem, you find the value of the alternating component and the mid-range value. And just represent it on this graph. Suppose this is sigma M, this is sigma X. This is the point that I have. So if the point is inside this region, we are going to have infinite life. So any point in this region is going to see the infinite life. But if the point is here, if the point is outside of this region, then we are going to have finite life, or basically we can say failure occurs. This is how you can predict the failure of components. Makes sense? All right. So it has some details. Make sure that you are following the steps. Before I go further, let me just talk about dealing with the fatigue concentration factor. We talked about Kf when we have completely reverse cycles. And Kf is going to apply to the nominal stress. And we are going to get the sigma max if you multiply the nominal stress multiplied by Kf. But this was valid for complete reverse cycles. When we have sigma A and sigma M, you calculate Kf and you multiply Kf times sigma A. So, and you will get sigma A max, same as before. But for Km, for sigma M, what should we do? Should we apply Kf to this one and get sigma M max, or should we do it differently? So there are some methods dealing this problem. We are using this one, Dowling method. So it defines Kfm, fatigue concentration factor for a mid-range stress. Kfm, it's going to be equal to Kf if this is valid. You will find sigma max for the from here. You multiply by Kf absolute value if this is greater than less than Sy. If this is less than Sy, then you go with this equation. Set it Kfm equals to Kf. But if it's greater than Sy, Kf should be calculated by this equation. And if this one is valid, this ratio, this expression is greater than 2 times Sy, the mid-range stress is not gonna show up. So sigma m max is gonna be 0 times sigma m. You will end up to the completely reverse cycle problem. So make sure that apply KFM if you have any discontinuity on the component. And this is how you can apply KFM. For KF, it's for sigma A, it's obvious. You find KF, you multiply by sigma A, you will find sigma A max. But for KFM or for the mid-range, it's going to be different. So you have to find KF. This is one important thing that you should consider when you do the stress analysis. Now, let's back to the failure theories. I would like to define a load line. If I connect the origin to this point and continue, I will get the load line. This load line has a slope. It has a slope. The slope is represented by R as this length, which is sigma A divided by sigma M. Sigma A divided by sigma M. It's going to be the slope of load line. If you draw this line and extend and find the intersection at this Goodman line, the intersection on the x-axis is gonna call SM, and on y-axis is gonna call SA. SM and SA. I'm just defining some terms. I'm going to use them later. So sigma A is the alternating components coming from here. Sigma M is a mid-range or mid-stress terms coming from here. SM and SA coming from intersection of load line and the Goodman line. Now, let me introduce yield line or Langer line. Sigma A, sigma M. So if this is Sy, and this is Sy as well, yieldless strain, yieldless strain. If you connect these two, it's called yield line or Langer line. If you have fluctuating stress, meaning you have sigma A and sigma M showing up in the problem. If the loads that you have, sigma M, sigma A, and sigma A, is inside this region, no yielding is going to occur. So you should be safe. But if this point is outside of this region, yielding occurs. So we have failure due to the yielding. So this is another thing that we should know. Now, I have these two lines on one region. on this curve. So this is a Goodman. This is a yield line. Let me just label some points. Point C is this point. Point F is this point. Point D is the intersection of these two. And point E is going to be this point. C, D, E, and F is going to be the points that I define. And this point is G. If I want to have infinite life and no yielding, I would like to have infinite life and no yielding. Which zone should be selected? So if you look at this figure, if I want to have infinite life, I should be on this side of the Goodman line. So to have infinite life. But at the same time, if I want to have no yielding, I should be on this side of the line, which is going to be this part. So it's going to tell me this region if the point is going to be located on this region, then we are going to have infinite life and no yielding alpha. So C, D, E. If you just care about infinite life, and don't care about yielding, then C, G, and O is going to be the area that you are looking for. C, G, O, C, G. It's going to include this portion, which we have yielding, but we don't care about the yielding, so we can cover that part as well. And if I don't want to see yielding, plus the number of cycles less than 10 power 6 means finite life. If you have this situation, if you want to have no yielding plus n less than 10 power 6 meaning finite life. And no yielding, it should be on this side. Finite life should be on the upper side. So CFD is going to be the area that we are looking for. No yielding because it's this side of the line, but it's a finite line, so it should be on the CFD. This is how you can So let me back to the Goodman line and talk about this quadrant. In this quadrant, sigma A is positive, but sigma M is negative, meaning we have compressive mean stress. The Goodman line is gonna is gonna have this line as a failure criteria. So this line, when it comes to the negative sides of the sigma m, it's gonna be a straight line. Can you tell me what does it mean, this straight line on the second quadrant? Say it again.
As long as you're under SE, you'll have it, right?
It means no matter how much mid-range stress you have, as long as sigma A is less than SE, you have infinite life. Sigma M doesn't have any effect. So here, sigma M can be this amount, but as long as sigma A is less than SE, you should be safe. So, or meaning sigma M doesn't have any effect on failure. So if you do the analysis and you calculate sigma A and sigma M, and sigma M is negative, so you are gonna switch to the completely reverse cycles, because this is not gonna work. I mean, this line is not gonna work. So you are gonna back to the completely reverse cycle. Back to completely reverse. So this is another thing that we should talk about. We should say about the Goodman line. Any questions so far? All right, on Wednesday I'll continue on the Goodman, and then I'll introduce the other 3 or 4 more theories about the fatigue failure analysis for for fluctuating stress components.